For the next few minutes, we're going to talk about converting power and voltage ratios to decibels.
Please see the video description for a full list of disclaimers, including the ones here, plus a timeline and helpful resources and links. Please support the channel by using our affiliate links.
Radio frequency and wireless engineers typically use decibels, or dB, to represent power ratios such as the gain of an amplifier or loss introduced by attenuators, cables, filters, or other passive components. We can also express absolute power levels in decibels by representing the ratio of an absolute power to a reference power level, such as 1 milliwatt or 1 watt, in decibel units. Once these numbers are expressed in decibel form, they are much more convenient to use in calculations, because in decibel calculations, addition replaces multiplication, subtraction replaces division, and multiplication replaces the operation of raising a number to a positive or negative power. Decibel values are moderately sized, positive and negative real numbers, typically, if not always, between negative 300 and positive 300 for RF applications. Numbers in this range are more familiar and easier to work with than the very large and very small ratios and power levels that are encountered in wireless systems. Although decibels are typically used to represent power ratios and absolute power levels, we also need to be able to use decibels when we are best able to obtain voltage levels, for example by using a voltmeter or oscilloscope, rather than power levels. We'll take a quick look at how to calculate dB from power levels, and then we will see how we can do the same thing using voltage levels. First, we'll take a look at converting power ratios to decibels. The formula for calculating decibels from power ratios is shown here. So first we take the ratio P2 over P1. We want to convert that to decibels. And that is 10 log 10 P2 over P1. Now here P1 and P2 are measured in units such as watts or milliwatts or some other multiple of a power unit, and we're converting them to decibels, which are a nonlinear unit or a nonlinear way of representing ratios based on the logarithm base 10. If we take only the logarithm base 10 of the power ratio, that would give us the ratio expressed in bells. Decibels are a unit derived from bells, where 10 decibels is equal to 1 bell. So the number of decibels is given by 10 multiplied by log base 10 of the power ratio. Now we'll look at an example. In this case, we're going to be calculating the gain in dB from input and output powers of a device. In this case, we'll consider a low noise amplifier, which we represent with this triangle symbol, and we have an input power of 10 to the negative 12 watts. And that's 1 picowatt. And an output power of 10 to the negative 9 watts, and that's 1 nanowatt. In this case, the gain of the low noise amplifier is given by 10 log 10 of the output power divided by the input power and this is equal to 10 log 10 10 to the 3, or log base 10 times log base 10 of 1000, and by definition the log base 10 of 10 to the 3 is 3, so this just gives a gain of 30 dB. We might also write this as 30.0 dB or 30.00 dB, depending on the number of decimal places that we're using in our calculation. We're also going to consider converting voltage ratios to decibels or dB. And we'll start with the same formula for converting power ratios to dB. And we'll also use the this equation that relates voltage to power. So we can express power in terms of voltage and resistance. And in this case, V is voltage across a load resistance. And here's our voltage. Now, if V1 and V2 are measured across the same resistance, R, So we'll assume that, then P2 over P1 in dB is equal to 10 log 10 V2 squared over R divided by V1 squared over R, and we can factor out the R's in this case because the resistance is the same for both, so this is equal to 10 log 10 V2 squared over V1 squared. Now there are a couple of ways we could look at this, but one is that there's a property of the logarithm that log x to the a equals a log of x. And so we're going to use that in just a minute. So we're going to just go back to our calculation. And we can square the entire expression V2 over V1, and so that that then becomes 20 log 10 of just V2 over V1. And this is the way we convert a voltage ratio to dB. So we can also write that as V2 over V1 in dB. And again, we're making that assumption that the input and output resistance of the device that we're measuring, or at least the reference resistance for each of the voltage measurements, are the same. Okay, so there are a couple of points to note here. One is that loads and device or component inputs and outputs in radio frequency systems are more often characterized in terms of impedance, which is represented by the letter Z, and that consists of a resistance and an imaginary component called a reactance that accounts for energy storage and phase shifts that are caused by that. And in electrical engineering, we most frequently use lowercase j as the symbol for the square root of -1, rather than lowercase I, because lowercase I is often used to represent a time-varying current. Impedance is a complex number, as you can see, and that accounts for a phase shift between current and voltage that occurs due to stored energy in components such as inductors and capacitors, and also in circuits that have inductances and capacitances within them, whether they're discrete components or not. And in the above derivation, we assume that X, or the reactance, the imaginary component is very small, and in this case Z is approximately equal to R, and the reactance term can be neglected. So for our derivation here, we're assuming that Z is approximately equal to R when X is small relative to R. And we can also express that as just X is much less than R. We're going to look at an example in which we'll calculate the loss in decibels from the input and output voltages of a radio frequency component. We're assuming that the input and output impedances are equal and real, that is, Z out equals Z in equals R plus J0. In this example, we'll consider an RF attenuator, and it has an input voltage of 150 millivolts and an output voltage of 10 millivolts. The input and output impedances are both equal to 50 ohms, which is common impedance used in radio frequency and wireless communication systems. Another impedance that you'll see frequently is 75 ohms, which is used in television systems, including cable television. So we're going to calculate the loss in decibels. And the loss is the inverse of the gain. So the gain is output over input. The loss would be the input over the output, or in decibel terms, it'll be the negative of the gain. And if we were expressing this as just a ratio, the loss would be the reciprocal, or 1 over the gain. So in this case, we can write the loss as negative V out over V in decibels, and that will be negative 20 because we're using a voltage ratio with a common resistance reference. We'll use 20 times log 10 of the voltage ratio V out over V in. And because we're calculating a loss and not a gain, we have a negative sign here. And alternatively, we could write this as 20 log 10 V in over V out. So what we've done here is removed the negative sign, but we've changed the order. We're using the reciprocal of this ratio, and that has the same effect as removing the negative sign. So we can express the ratio in dB this way as well. Now we need to plug in the numbers and We have 150 millivolts divided by 10 millivolts, and that will be 20 log 10 of 15 when we do this division here. And that gives us .52 dB. And that's the loss due to the attenuator. Now, it's possible that we'd be working with fewer than 2 decimal places. It's unlikely that we would use more than 2 decimal places, as you'll see in another video. But this is the answer that we get, and that's a power ratio of about 200. So the close to 200, but not but not exactly. So, and we'd expect that because if we were to square these, this would be a 10 log 10 of 15 squared, which is 225, and so it's close to 200, which is 23 dB. This is what we get. To summarize, power ratios are converted to decibel units by taking 10 times log base 10 of the power ratio. For voltage ratios, the decibel equivalent is 20 times log 10 of the voltage ratio. The expression for voltage ratios assumes that the impedances across which V2 and V1 are measured are the same, and the resistance is the same for both Z1 and Z2.
Thanks for your time. Please hit like and subscribe and support the channel by using our affiliate link if you plan to buy a featured item. We also provide consulting services and referrals.